Right, that'd be good. First of all, the disclaimer. Sorry I can't be up there. I really enjoyed last time I was seeing you. And the disclaimer is I'm not a planetary astronomer. I'm not a Pluto expert. However, I think this is a great story. It's interesting. It tells you how science develops and changes. And it's also still controversial with some people when I give these talks. So it's really quite interesting for me as well. So first of all, where I'm from, the Royal Observatory, Edinburgh, University of Edinburgh, although I'm now based in Preston, so it's a long way away from where you are at the moment. But I suspect it's just as wet outside. It's certainly pouring down here. So this talk is not about the dog, although you'll see the dog comes into it towards the end of the story in terms of the emotional attributions. So just let's get up to speed. Planets in the solar system. We know there are 5 naked eye planets. And then we had the first telescopic discovered planet, Uranus, in 1781 by William Herschel, which is an interesting observation. Uranus had been seen by a number of astronomers beforehand, but it was Herschel who was careful enough and conscientious enough to actually note it and plot its orbit, although it didn't move very much, but nevertheless he could see it was not a star and it was a moving object. And so Herschel gets the discovery of Uranus in 1781. Now, as time went on and astronomers actually started plotting its orbit out, they started realizing this orbit wasn't following strictly Newton's laws. It looked like it might have been perturbed by another so-called invisible planet. And so this is how the planet X, which has started off the whole, this gamut about Pluto, started off. Now, a French mathematician called Leverrier, who was an absolute genius, he worked on Uranus's orbit and the perturbation of Uranus's orbit. In 1846, he calculated and published the position of this new planet X. And the next night, Neptune was immediately discovered, which is a fabulous bit of calculation and also subsequent observation. But following this, there was still some debate about the orbit, and there was possibility of yet another planet. The famous planet X came into being. So Percival Lowell, who was the director of the Lowell Observatory in Arizona, he made it his mission to search for planet X. He did this from 1906 until 1915 when he died. And then, although his wife wanted to continue this, it fell into a legal impasse with the denizens of the observatory, and she couldn't get access to the data in which Lowell had used. And so eventually this was solved, this legal impasse was solved. In 1929, she appointed Clyde Tombaugh to do the search for Planet X. And he had a secret weapon, which was a blink comparator, which I'll talk about in a moment. And lo and behold, within a year, he discovered Planet X, which will become known as Pluto eventually, in January and February 1930. And there's always some question about whether this was just by chance, because it certainly wasn't in terms of the same magnitude as the work by Leverrier, who pointed a position, and there it was. So nevertheless, it was a discovery. This is Clyde Tombaugh, who's a young man, an engineering graduate, but keen on astronomy. And this is his own Newtonian telescope, not what he used for observing Pluto. But this is the blink comparator. Now you can see, hopefully you can see, there's a plate here and a photographic plate there. And these are of exactly the same piece of sky. And there's a series of optics here and a series of optics there. And then a flip mirror in here, and you stick your eye to this eyepiece here. So you look through the eyepiece and you flick between the two images. And the eye-brain combination is really excellent at figuring out if there's any change between the two pictures. And lo and behold, this is the discovery image. Now on the left-hand side, you will see, although this is much easier on a zoom image than actually shown in most holes that I find. You see the star on the left, just there, the little object in this sort of quadrangle of stars here with the one in the middle. And if you come and find the same quadrangle and the one in the middle, you see that little object is not there, but it's appeared over here. These are about 6 nights apart, and this was the motion of Pluto on the sky. And these were the discovery images of Pluto. So you see, it's not easy to do. The blink comparator makes it much, much easier. And as I say, Pluto had been, just like Uranus, Pluto had been seen before by a number of astronomers, but not recognized as the planet that it was in the discovery image. So now we come to the naming of Pluto, which is where Disney comes in. And there's no real evidence that the Disney, the dog, and the Pluto had any links with each other whatsoever. Instead, the Lowell Observatory, who had the naming rights, they asked for volunteer suggestions. And they got over 1,100 suggestions, which they whittled down to a short list of 3 names for a staff vote, which came up with Minerva, Cronus, and Pluto. Now, Pluto had been proposed by a Brit, an 11-year-old Oxford schoolgirl, Venetia Burney. And although she didn't send them the information herself, she told her grandfather, who told the chair of physics at Oxford University, who passed the information to the Lowell Observatory. But nevertheless, it was an out-and-out unanimous choice. Pluto, god of the underworld. And also maybe because PL like stands for Percival Lowell, so the PL got a little link in there as well. And interestingly enough, this continued the link between particles, or not elementary particles, but atoms and planets in the solar system. Because when Uranus was discovered, uranium was discovered only six or 8 years later, and hence it got the name uranium. And then when essentially Neptunium was discovered in the 1940s, that was named after Neptune, the next nearest planet. And so when Pluto was discovered, then when plutonium, the element, was discovered in 1941 or 42, then it was called plutonium. So that's a nice uranium, Neptunium, and plutonium in terms of physics. So what do we know about Pluto? So we'd like to know certain things about key parameters. How big is it? How heavy is it? And what's its orbit look like in terms of a solar system thing? So let's start off with its mass. Okay, 1931, by calculating the effect on the orbit of Neptune and Uranus, it was meant to be about the Earth mass. But the trouble with this was there wasn't a huge amount of data on the Neptune and Uranus orbits because they hadn't been discovered long enough to get a good baseline. But this is about Earth mass. In 1948, Gerard Kuiper, he worked out about, well, he thought he worked on the diameter, which was about 10% of the Earth's mass. And this is essentially translated into a mass and diameter. And this makes Pluto about the same size as the Earth, or the mass of Mars. Now, in 1976, this was a breakthrough measurement by Dale Cruikshank et al. From the University of Hawaii. They discovered that the reflectivity of the atmosphere of Pluto was methane ice. And that means what you look at, the object is very, very bright for its size, which actually means it's bright, but it's only about 1% of the mass of the Earth. So it actually becomes a very negligible body altogether. In 1978, discovery of the moon going around Pluto Charon, and the orbits then gave 0.02% of the Earth, which is crazy. So Pluto, all of a sudden, is shrinking in mass. It's getting very, very light. And there were huge doubts about, was this Planet X, if Planet X really existed? And if we look on this graph, look on the y-axis going up here, this is the Pluto's estimated mass in Earth mass units. So this is the mass of the Earth going across here. And this is the year which we're talking about. So when Pluto was discovered, essentially, it was really quite massive, but the Earth mass coming down here, this is just Planet X guessed at in terms of earlier studies. And then as time goes on, effectively, Pluto's mass just gets smaller and smaller and smaller. And in that sense, it should have vanished by now altogether. And the trouble was, with better calculations of the orbits, the reason for having a large planet out there perturbing Uranus and Neptune, that reasoning essentially vanishes. And once the Voyager probes went to the outer parts of the solar system, the necessity for having a Planet X actually disappeared altogether. So that was an interesting aspect, and so how science moves on with better observations. So let's now go back to looking at Pluto. What about Pluto, its size? It's actually not very massive, as we've seen, and it's far too small to measure directly until very recently. So how do you make estimates? Well, the trouble is you've got the albedo, the reflectivity of the atmosphere. You've got to guess what that is. And then they sort of had a good idea of what it was with methane ice. So then you've got the density. So if you know the mass and you know the atmosphere, then you can work out the density. If you can guess the density, then you can work out the mass, then you can work out the size of it. So it's all a question of free parameters, which make it difficult. The best estimate now is 2,374 kilometers. And this is direct measurements from New Horizons, which we'll talk about at the end of the talk, the New Horizons space mission. But 2,374 kilometers is very, very small compared to the other planets. Now, how small is this? And I confess that not being a planetary astronomer, I really, until I started doing this talk, had no idea how big Pluto really was. But actually, Pluto is tiny. It's smaller than the moon. So here we have the Earth, Pluto, and the moon. So it really is tiny. And if we look at the Galilean satellites and Titan, large satellite of Saturn, and Triton from Neptune, you see Pluto is really quite puny compared with all of these moons. And so people were then starting to question whether this really was a planet. Was Pluto really the 9th planet? So before we get to that, what about Pluto's orbit? Well, it's got a semi-major axis of about 40 astronomical units, so 40 times the distance of the Earth to the Sun. The orbital period is a staggering 248 years, so it's a long, long time to get around the orbit. But the eccentricity is 0.25, and that's very strange because for all the other planets in the solar system, the eccentricity essentially is a circle. And this thing is quite eccentric. And furthermore, the inclination is 17 degrees, so it's inclined to the plane of the solar system, whereas all the other planets are within 2 degrees. This really is a flat plane compared to Pluto. This gives you an example of it. So here we have essentially, although they look squashed out, it's just the way we're drawing it on the screen. We have essentially the solar system of planets, and then Pluto with a very elliptical orbit and highly inclined. So Pluto stands out as being different from everything else in the solar system. And then the question is, well, is there anything with similar orbits to Pluto's? And the answer is, well, the Kuiper-Edgeworth belt of small bodies, reservoir perhaps for comets or centaurs or other things. This has been essentially proposed between 43 and 51 as this regime of small bodies, but never really observed. But it might have been the beginning of them. And then in 1992, everything changed. And this essentially is where I started getting interested in what was going on. It was discovery of the first Kuiper belt object called KBOs by Dave Jewett and Jane Liu of the University of Hawaii. And this was called Albion. And so this was the first discovery and discovered in Hawaii. We now know there are more than 3,000 of these Kuiper belt objects. And it's just obviously the tip of the iceberg. There must be hundreds of thousands of them out there. So what do we know about Kuiper belt objects? Well, astronomers love to classify everything they get their hands on. And the Kuiper belt objects come in various forms. Cold, which are circular and non-inclined orbits, just like the planets, or many of the asteroids. There are hot Kuiper belt objects, which have elliptical and inclined orbits, and we'll see Pluto is one of these. Resonance ones, orbital locking with Neptune, and Pluto suffers from orbital locking with Neptune. It's in a 3-to-2 resonance with Neptune. When Neptune goes around twice, Pluto goes around 3 times the Sun. And then it's scattered, it gets too close to Neptune, and this could be like a centaur in terms of that. They get battered all over the place. Another name for these KBOs is trans-Neptunian objects, objects that are farther away than Neptune. These are called TNOs, and I will use these interchangeably throughout. This is an example of the solar system. Pluto is looking down on it, so you can see the circular orbits. Pluto is the magenta orbit. And then we have Eris out here on a very elliptical orbit, which we'll talk about. And then we have Sedna on a hugely, hugely elliptical orbit. And these became very important, as we'll see. So this is an example now of an artist's impression of Kuiper belt objects. And you'll notice many of them have Hawaiian names, Maki Maki, essentially, because many of them discovered in Hawaii by the University of Hawaii. But you see, Pluto fits very well within all of these. And Pluto and Eris are essentially about the same size. And so this also caused some chaos. So the impact on this for Pluto was quite noticeable. Discovery in 1978 of a big moon, Charon, which was different to anything else in the solar system. We'll talk about this a little bit later. And by mid-1990s, the planetary status of Pluto was being questioned, particularly by Dave Jewett. And this is, as I say, where I came into it, because I was in Hawaii, essentially being the director of JCMT and Joint Astronomy Center. And Dave Jewett came across from Honolulu and gave us a seminar, which was on status of Pluto and Kuiper Belt objects. And it was very clear when he presented this that he had no doubt about the matter whatsoever. Pluto was a Kuiper Belt object, not a planet. And I have to say, everybody else in the audience was equally convinced as well. And by 1999, there was a proposal to the International Astronomical Union, which again we'll come back to, which was held in Manchester then, to reclassify Pluto as something else but not a planet. And the IAU, probably quite justifiably, took one look at this and decided this was far too hot a potato to get hold of, and so sort of binned it and said, no, we're not going to do that at all. And so the next thing that happened was in 2000, the Hayden Planetarium became the Rose Center in the American Museum of Natural History in New York when it was refurbished. And when they put the solar system back up hanging from the roof, Neil deGrasse Tyson, who was the director, and you may have heard of him, he does lots of outreach on American TV, is the US version of Brian Cox, except he's an astronomer. And Neil deGrasse Tyson omitted Pluto as a planet, and there was a huge retribution and hate mail for deGrasse Tyson for doing this, demoting Pluto. So that was a hint of things that come. This was not going to go down well with many of the general public. And then also in 2003, another TNO KBO, Eris, was discovered. And this looked at the time to be bigger than Pluto. It's at the time, I mean, now we think it's about the same or slightly less than Pluto, but nevertheless, it was of the same size as Pluto. And this was discovered by Mike Brown, who was a famous planetary astronomer from Caltech. And so was this then the 10th planet? Although I must admit, Mike Brown kept really quite quiet about calling it the 10th planet, but other people essentially questioned whether it was the 10th planet. And then also in the same year, Sedna was discovered by Mike Brown, and was it his 11th planet? Sedna has this hugely peculiar orbit, and we'll see this has got odd, as we see later on. So let's go back to Pluto and Charon, the double planet, as we'll see later on. This is an HST image using the faint object camera, and it's the only thing that can do it apart from sending a mission there, like New Horizons. So here we have Pluto, and here we have Charon. Now, the interesting thing is Charon is significantly big compared with the size of Pluto. And the center of mass of this system lies about here, which is different to everything else in the solar system. For all the other planets in the solar system, the center of mass of the planet and of their satellites lies inside the planetary body. So it does for the Earth, it does for Jupiter, it does for Saturn, it does for everything else. But in Pluto's case, the center of mass is here. So Pluto rotates about this point, Charon rotates about this point. So they're like a rotating dumbbell pair in space, and that also makes them different. So now we come on to the debate of the status of Pluto, the International Astronomical Union, the IAU. This was founded in 1919, so it's essentially just over 100 years old. It's the world's largest professional body for astronomers. It's got about 10,000 members, depending upon how you count it. Has a great mission to promote and safeguard the science of astronomy and all its aspects through international cooperation. And though I'm going to be slightly rude about the IAU, I feel I can do that, seeing as I was the Assistant General Secretary for a year. So I feel I can at least be fair about this. Now, it's the internationally recognized authority for assigning names, nomenclatures, and designations to celestial bodies, new asteroids, surface features, craters, rims, canyons, whatever. The IAU is the official body for naming or for recognizing these names. And one thing the IAU does for a normal astronomer is every 3 years, it holds a big shindig of a meeting, which lasts 2 weeks. It travels around the world, it's held every 3 years, and it's one of the most diverse astronomical meetings with essentially many hundreds, if not thousands of people actually attending these. And they have all the topics that are ranging from the solar system to supermassive black holes, gravity, you name it, they have talks about it and seminars about it. So IAU recognized it was going to have a problem with Pluto. And in 2003, they agreed that they would make 2006, the General Assembly, which was being held in Prague, this would focus on Pluto. Was Pluto a planet or not? So like all good organizations, they set up a committee to look at this, a planet definition committee. This was set up in 2004. But interestingly enough, the IAU already had what was a Division 3. They had many divisions on quasars, radio astronomy, planetary system sciences, which was Division 3. And Division 3 definitely wanted to have their say, although it looked like the executive had sort of chopped them out of decision making. So they had a definition committee charge. This is what the committee had to work on. So 1, discussing the broader social implications of any new definition of a planet and recommending a course of action that balances the scientific facts with the need for social acceptance of any change. Note that word, social acceptance. 2, addressing the status of Pluto under the newly discovered TNOs in the light of recommendation 1. And 3, considering whether the current naming procedures for planets and minor planets have exacerbated the problem of defining a planet and recommending whether revisions are needed. And 4, attempting to frame these recommendations as a resolution or resolutions that could be put before the Prague General Assembly in August for voting on and for possible adoption. So here we have, this is the committee which was going to sort out, was Pluto a planet and are we going to vote on it? So we then move on. The president of the IAU, Ron Eakers, a famous Australian radio astronomer, and he came out with a very interesting statement and said, from time to time, the IAU makes recommendations on issues concerning astronomical matters affecting other sciences or the public. Hence, IAU recommendations should rest on well-established scientific facts and have a broad consensus in the astronomical community. And I think people couldn't disagree with that. So the Planet Definition Committee came back really very, very quickly with an answer and said, whoa, this is simple. A planet is a celestial body that A, has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium, in other words, nearly a round shape, and B, is in orbit around a star, but is neither a star nor a satellite of a planet. So in other words, it's big and round. And that's essentially what you've got. So the IAU thought, well, if we crack this, no problem. How hard can this be? Dead easy. But they thought, well, this could have implications. And so they very sensibly appointed a press officer 6 months before the General Assembly. And this, again, is where I get linked in, because it turned out the press officer was the secretary of the Commission of the IAU on communicating astronomy with the public. And I was president of that, and the press officer was my secretary. And he was a great guy, and he really genius at doing this sort of thing, genius outreach. And so they worked on this, and they got a really good person. And the executive committee for the IAU, this is a wise group of men, and I think it was all men at the time, this wise group of about 8 men, and the essentially general secretary and the president, they came up with a proposal. And so they looked at what the essentially Planet Definition Committee had done, and they said, okay, we're going to propose 12 planets with potentially more to come. So there's 8 classical planets, that's everything going out as far as Neptune, 4 planets in a new and growing category of Plutons, which is Pluto-like objects, which is Pluto and Charon, a double planet, Eris, a TNO, and Ceres. And you're thinking, hang on, Ceres is an asteroid living around inside Mars orbit. And this is true. And Ceres, when it was first discovered in about 1801, had been thought to be a planet, another planet of the solar system. And it was only when more asteroids were discovered, about 50 years later, that Ceres was demoted from being a planet to an asteroid. But Sedna wasn't on this list, and so people were saying, well, where's Sedna? So then we get to the General Assembly of the August the 14th to the 25th in Prague. And my friend, the press officer, came to me on the Sunday night before the meeting really begins and said, here's the embargoed press release which is going to be issued tomorrow for people to report on. And the embargoed press release essentially said, just the paragraph above, 8 classical planets, double planet, etc. And I took one look at this and just said, it's never, ever going to fly. I mean, I'm just an ordinary bog standard astronomer, but you knew this wasn't going to work. Sticking Ceres in there, missing out Sedna, having Pluto, Charon as a double planet just wasn't going to fly. And so, I just said, and he was totally shocked. He said, well, they have to agree with this. It's been said by the executive. Naive press officer, since when do astronomers paying attention to executive committees? So, this I thought this is going to be real good fun. So I decided, instead of going to my topics on supermassive black holes and AGN, I'd go to all the solar system talks. That's where the action was going to be. So this is the famous diagram of the solar system. And I like this because although they're to scale in terms of size, they're clearly not to scale in terms of distance from the sun. But it's a really good example of the scale of the size of the body in the solar system going out. Now, you probably can't see Ceres. I can only just see it as a single pixel on my Zoom screen. You might struggle from the audience, depending on your projector. And then we come Pluto and Charon out here. And we come, this is Eris out here. And Sedna doesn't appear on it all. But it's a very famous picture, this, as we'll see later on. So the IAU were very understanding of knowing to keep the press on board, recognized the potential impact. They made major efforts in terms of having web pages, lots of information, question answer links to the press, putting astronomers up to talk to the press. And they wanted to make sure that it was a transparent and open process of scientific debate. This was science in the real world working. And this is an example of the press room. And this gentleman here is Owen Gingerich, a famous historian, astronomical historian, good guy. And he was chair of the Planetary Definition Committee. And so the first plenary meeting, which was on the Monday, where everybody gets together in a major hall and auditorium, showed this is going to be very, very contentious. The first meeting of Division 3, which was the Planetary Definition Group, was on the Tuesday. And I got there really early, but there was standing room only, people pressing in the door, listening in the corridor. And this was another ruckus meeting. Lots of people were very against Pluto and Charon double planet, unique in the solar system, on your bike sort of thing. Major disagreements about the definition of a planet. Division 3 wanted a further point to be added. A planet must have cleared its orbit. Now, I'm sure to me and many other people in the audience, we'd never ever heard of a planet has to have cleared its orbit. But this planetary dynamicists, and there's a whole bunch of them there, and they were all, I hate to say this, they're all old and they're all men and spent their lives working on planetary dynamics, but they were absolutely adamant a planet must have cleared its orbit of everything else, otherwise it's not a planet. And this didn't go down very well with the Division 3, with the New Horizons mission people. So Alan Stern, who was the PI of the American mission to go to discover what there is to learn about Pluto, the mission called New Horizons, he was furious and he made a counter proposal and an email petition against this idea of Pluto being demoted from being a planet. And this gathered over 200 names, which wasn't bad at the time. And then people said, well, hang on, the clearing of the orbit rules out Neptune because of centaurs, and it also rules out Jupiter because of Trojans. But we'll come to see this is all depending upon resonances. And here we go, Jupiter and the Trojans and resonances. And here we have the complicated diagram of the talk. This is the complicated diagram. Here we have the sun in the middle, and here we have a planet. And in this case, we can call it the Earth, just for, I'll tell you why in a minute. And so you have these L1, L2, L4, L5, and L3 points, which are stable points, which means if you put a body here, it will tend to stay there, working its way around the sun in a stable orbit. And if you then have L1 and L2, and you put them in L1, L2, or L5, or L4, or L3, they will remain where they are in relation to the planet. So the planet goes round, L1 and L2 go around with it, so does L4, L5, and L3. And you will notice that L2 is the Lagrange point to which the many missions in astronomy are sent because they then just stay there and you don't use a huge amount of energy in propulsion systems. And that's where JWST has gone, about 1 million miles away, or 1 million kilometers away from the Earth. And that's the L2 position. So if we move out and call this planet Jupiter, then you find there are a bunch of asteroids at L4 and a bunch of asteroids L5. They're not all sitting there, they sit in a heap, but they're in stable orbits and they don't go anywhere else. They're the orbit in terms of these ellipses like this. And these are called the Trojan asteroids. And this is an example of the Trojan asteroids. We have here Mercury, Venus, the Earth, and then Mars. And then we have Jupiter and the preceding Trojans and the receding and seeding Trojans. And we've sent a mission called Lucy to investigate the Trojans. This was launched 2 years ago in October 2021, and it has a very complicated way of getting there. It will arrive in 2027 to the leading orbit, and it will sample by flyby essentially one of the leading objects. Then it will fly back, do a fly past the Earth and whiz out again and look at the trailing bodies. And that will be in 2033. So it's only 4 and a bit more years to go before Lucy gets there. So we'll learn a lot more about the Trojans. So we've already been sent there. So people said, well, these violate the idea of Jupiter being a planet. It's not, it's because of resonances, and these are stable orbits. So the reaction at the IU. So the next Division 3 session was very, very, very stormy. And in fact, everybody knew it was going to be stormy. And so it was moved from its small lecture theatre to the main auditorium. So it had plenty of space for everyone to go. And everyone went and just ignored all the other talks, essentially. And there were lots of very passionate speeches, both for and against Pluto being a planet. Resolutions were made, being changed in real time. The chairman was clearly losing control, and people were getting quite irate with him because they were saying he was biased. And of course he was biased because he'd come out with one of the definitions in the first place. And so then we had the final plenary session on Thursday, the 24th. And this was the vote. Lots of comments and still confusion about the status of Charon. It was a packed session, but unfortunately I had to leave. I had to go back to Edinburgh, so I flew back on the Wednesday. But I was watching what was going on because the European Southern Observatory had a video feed going on. And I had a colleague in the audience who had a mobile phone, and he was telling me on the phone exactly what was happening. So it was really good. The star of the show was our own Justin Bell Burnell, and she essentially calmed the entire audience down, and she presented her props with poor Pluto as the dog, and all the other planets, the umbrella sitting in there, essentially the family of planets, and the cereals, which was meant to represent Ceres, though she agrees that was not a very good option in the end. So the final resolution, and here we have it. The IAU therefore resolved the planets and other bodies in our solar system, except satellites, be defined into 3 distinct categories in the following way. A planet is a celestial body that A, is in orbit around the sun, B, has sufficient mass for its self-gravity to overcome rigid body forces, so that it assumes a hydrostatic equilibrium nearly round shape, as we had before, but C has cleared the neighborhood around its orbit, so Division 3 got their way. A dwarf planet, a new definition, and this is where I think it's a total cop-out. A dwarf planet is a celestial body that A is in orbit around the sun, etc., 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 to get to C, has not cleared the neighborhood around its orbit, and D is not a satellite. So it's a small round body, but it doesn't fit in with the other categories. And so we're going to call this a dwarf planet. Although I have to say, I find very few people referring to these things as dwarf planets. Everything else, except satellites orbiting the sun, shall be referred to as small solar system bodies, but all the people I know still call them asteroids. So then there were amendments, which I will briefly skip through. Insert the word classical before the word planet. Pluto is a dwarf planet by the definition recognized the prototype of new category of trans-Neptunian objects, quite important. And add the sentence, this category is to be called Plutonian objects. So people had to vote. And so they had to vote by showing these yellow cards. And this is the audience, the General Assembly audience. And these are the votes on the screen. These are the words on the screen, just like you've had them. And people had to vote in every single one of these amendments and results. So the resolution was passed with overall majority from the audience. So done deal. No Pluto anymore. being demoted to dwarf planets. First Amendment, add the word classical, show of hands against, rejected. Second Amendment, Pluto is now a dwarf planet and a new breed of TNOs. That was passed. And the final one essentially failed with 183 versus 186 Plutonian objects, which is almost a dead heat as far as I can see. Big negative reaction from the public. Huge emotional connection with Disney's Pluto, particularly in the USA. The scientists pointed out this was non-democratic. Only 5% of world astronomers actually voted on final session. Only 400 members, man. I was one who had gone home, so I couldn't vote. Lots of negativity from the US, not only the public, but the scientists. European partisan was just like everything else. New Horizons team members were up in arms about it. And there's a wide range of press coverage altogether, which we'll see now. And New York Times had a very interesting, very sensible article about how do you define a planet? The debate continues. Nature, what are round objects, being the basis of planets? They've got to be round. New Scientists, down but not out, poor Pluto being demoted. Very interesting article. Nature, then, a very full-scale article inside. And this is the voting, and this is the General Assembly, and this is the Assistant General Assembly, the Vice President, and the President there. And so this was an interesting aspect. And here we have the American Science magazine reproducing the famous picture I showed you earlier on with a very sensible article. And then we have the other articles. This is the German Meinung, the opinion piece. Pluto is kind planet, which is what I think of Pluto not being a real planet, you know, up yours. And then we had the public, and there's lots of these newspaper cuttings, which I've only done a few of them. And I like this sort of protest for Pluto, size doesn't matter, icy ball thingy, not sure really, too small to matter, could have been a planet. And so these are really good. This is the instructions for a person on the planet. Hit the meteors at the back, try to win the meteors to hit other planets. So playing interstellar billiards with planetary systems. And what is this? We are what? We are a dwarf planet? Up yours. And then Pluto, 1930 to 2006, revolving piece. I do like this one, Pluto, proof that size matters. And so there's many lessons have been learned for astronomy in general by the IAU. It now has e-voting for contentious issues. So it realizes it wasn't democratic at all. An example of this is the recent 2 years ago now, but less dramatic IAU resolution of the Hubble law being recommended as the Hubble-Lemaitre law, which was done by e-voting. And let's now have a look at the New Horizons mission, the mission to go and see Pluto. This took off in January 2006, 6 months before Pluto was demoted. It flew by the Jupiter system in 2007. It got to Pluto in 2015, and notice it hurtled past Pluto and just kept on going to look at other Kuiper Belt objects, and it just whizzed past them. And so there aren't that many images of Pluto because it went past so quickly. But here we have the most famous of Pluto and the surface features blown up. And it's really, Pluto is a very, very interesting planet in its own right. That's a whole different talk, not to be given by me. And here we have Charon, which is also full of craters and rims and seas and things like that. So really interesting aspect. New Horizons discovered 4 more moons going around Pluto. So Pluto doesn't just have Charon. It also has Nix, Hydra, Styx, and Kerberos, all from the underworld, as you'll recognize, the scholars of you. Pluto also was found to have a very, very thin atmosphere. As well as having methane surface ice, it has a very thin atmosphere. And this is my favorite picture. This is backlit Pluto, showing the very, very, very thin atmosphere surrounding Pluto. A New Horizons mission went on to look at Kuiper Belt object Arakoth. And essentially, this shows you that clearly these two bodies have joined together under a slow, low energy collision and stuck. And this gives you, and then certainly some hope that this is perhaps how everything built up in the solar system by low energy collisions, building up mass over millions and millions of years. And so eventually you get what we have in the solar system. And I'm going to pass on this one. It's too complicated. So finally, speculation as to where we are today. Is there a 9th planet? Now we've demoted them down to 8. Mike Brown from Caltech still thinks there is. He thinks there's one 6 times the Earth, but 15 times farther out Neptune. So this is a big object. It was proposed in 2016 and based on the orbits of Sedna, or the disorbit of Sedna, not being a perfect Newtonian orbit. Most people, I have to say, don't believe this exists. They think it's a resonance again, and Sedna is affected by these resonances. However, there's a possibility there might be a planet in the Oort cloud, much, much further out. And talking of the Oort cloud, we have objects which come in from interstellar space, and here we have Oumuamua, essentially again Hawaiian name, which appeared suddenly in 2017. And this is the artist's impression of this thin pencil rock-like structure which came into the solar system, hurtled in and hurtled out again, missed everything, but came in with a huge velocity. And it was almost thin before we really noticed it was whizzing past us. And this has to be interstellar in space. And have to worry about this. So we know these things coming. And the Gaia mission, which is also sitting at L1 and mapping everything in the sky, essentially all the stars in our galaxy, looking at their motions, their proper motions, their velocities in 3 dimensions. And this is looking at star movements and plotting them and cataloging them. And it found an object, essentially a red dwarf star called Gliese 710. This has now been projected that it will now impact the Oort cloud going around our solar system in about 1.3 million years. There's a possibility for sending comets into the inner solar system as Gliese plows through the Oort cloud. Could this then be an extinction level event on the Earth? Well, we'll have to wait and see, but 1.3 million years, watch this space. Thank you very much.
That was excellent, Ian, and thank you very much for not having any formulas or mathematics. That suits me absolutely down to the ground. Now, I'm going to ask the audience for questions, but I'll give them a little bit of time to think. In the opening part of your talk, you said there was a really good mathematician that predicted, where the planet might be so that Tombo could, try and detect the planet. But I've gone through your talk. I'm starting to wonder whether it was just fortuitous that Pluto was actually discovered.
Well,
could it have been another KBO TNO if it had been another time, perhaps?
Yeah, it could easily have been. I mean, one of the things I say, if Pluto hadn't been discovered then, it would have been discovered in the early 1990s. So if people had just missed Pluto, there was a search on for Kuiper Belt objects. By the time 1990s, the University of Hawaii, Dave Jewett in particular, was searching for Kuiper Belt objects. And he knew what to look for and knew how to do it. So if Pluto hadn't been discovered then, it would have been discovered in the early 1990s. But then I make the point, would you have called Pluto a planet in 1992? And the answer to I'm really convinced you'd have just said, oh, it's a Kuiper Belt object because it looked so different. And I think it was only because it was discovered in 1930 that we essentially said, well, it has to be a planet. What else can it be? Not an unreasonable suggestion at all. Nothing wrong with that. But science moves on.
It does. Does anyone have any questions I can put to Ian? If you just tell me, I'll yeah. Okay, right. Ian, Dave's asked the question. He's going, given that the distance Pluto is from the sun will look star-like, if you were on Pluto. He's going, why do the shadows on Pluto look, as distinct as they are, considering the sun is so far away, basically?
It's just surface features. There's different surface features that have different albedos. So it's just the different rocks and different surface features and different methane ice on different parts of it. And why they are is still a topic of great debate. The planetary astronomers are still working very hard to try and understand what makes up the geology of the Plutonian surface. And that's essentially still really a modern topic of astrophysics, because it's very, very hard getting good data back from Pluto. It's on the New Horizons mission that really has shown us the data, and that there's only a limited amount of data that the New Horizons got because it whizzed through the system so quickly. It hurtled past Pluto and Charon and then just disappeared into the far distant parts of the solar system. So there's only a limited amount of work, but the geologists and the planetary astronomers, surface scientists are working very, very hard in terms of trying to understand the internal geophysics of Pluto as well.
I think another aspect what Dave's trying to ask is the shadow, right. Yeah. I don't know whether you can hear this, Ian, but Dave
No,
saying,
I couldn't hear that. Maybe I'm misinterpreting the word shadow.
No, it's because the microphone's facing me, and Dave's right. It's ignoring the albedo of the different geology. It's why are the shadows so pronounced? Consider, the intensity of the sunlight. Everything looks very, as if there's a big light close to it, so to speak.
Well, I mean, the sun is still bright. It's by far the brightest thing in the sky in Pluto, and so there's plenty of illumination from the sun to see essentially contrasts in terms of rills or mountain effects. There's still plenty of sunlight. Wouldn't keep you very warm, but there's plenty of, in terms of visible reflectivity, there's plenty of differences on there.
Okay. Any other questions at all? Any other questions? I've got just one last one for you, Ian. It's the vast amount of TNOs and KBOs that you described showed. Would they have a measurable impact on the orbits of the planets Neptune or Uranus or anything like that?
No, absolutely not. For two reasons. One, they're far, far, far too small, and two, they're also much farther away. So Neptune is actually quite big, and Neptune has a major impact on anything in its vicinity. So Neptune certainly has an impact on Uranus, and certainly Neptune has an impact on the asteroidal bodies called centaurs, which get anywhere near Neptune and they just get blasted off somewhere else. And some of the thoughts that some of the satellites of the giant planets, Saturn and Jupiter, there might have been scattered centaurs captured essentially by Saturn and Jupiter. One of the, given the fact they've got 60 or each of these tiny, tiny bodies, not the big Galilean satellite, but these tiny bodies going around them, that Neptune can really do havoc to the region out there. It's actually a big body.
Sure. Ian, can I just take this opportunity to, sorry, there's one more question. Sorry, I've got one more question. Okay. The question observation is, it's clear that Pluto and the other objects are at a certain inclination compared to, our planets, the rest of the solar system. Is there any reasons to why they are all in pretty much that same inclination?
Well, they aren't all in the same inclination. In fact, there's a very wide range of inclinations. The Kuiper Belt objects have inclinations going from 0. They're actually in the plane of the solar system to 40, 50, 60 degrees. So it's a big range of inclinations. The complicated diagram, which I didn't show in the end, actually was all about the inclinations of the centaurs and things like that. But I decided, looking at the clock, and you wanted to keep me to 45 minutes, I rather than explain that rather complicated thing, I passed over it. But in fact, that showed you the very big wide range of certainly inclinations. So they're not all like Pluto. Some are much higher, but also some are in the plane of the solar system. So they take a big wide stretch of inclinations.
Okay, well, thanks for that, Ian. Ian, can I just say thank you very much for your time. That was really, really most enlightening. There's a lot of stuff I didn't know at all, hadn't heard of. There was a lot of emotion, obviously, at that time. Probably still is. It's unfortunate you can't be up here with us. I know you would.
Yeah, sorry about that.
That's okay, that's fine. But we will make sure we give a token of appreciation. We'll get it sent down to you, so I'll get an address from you, Ian.
No need, no need.
We'll get something for you. We always recognise a good speaker. We always like to keep you on
Thoroughly
side.
enjoyed it.
That's great.
Thoroughly enjoyed it.
Well,
all the very best to everybody.
Thank you. We're away to get a cup of tea and have a raffle, and then do the rest of our club sitting. Thank you.
Enjoy. Thank you very much, everyone.